Hello everyone, I'm Siddhant and today I'll be presenting my machine learning project titled Airline Delay Prediction. The aim is to use data-driven modeling technique to predict which airline operations are likely to face high delay so that we can take preventive actions and improve reliability for the airline. Okay, so flight delays have cascading operational and financial effects, okay, which causes uh, majorly because of the weather and congestion of airlines, control issues like maintenance and crew management, and various other issues as well. Basically, our goal is to anticipate these risks before they occur, enabling proactive decision making. So, yeah, yeah. Uh, so, what basically is our objective? The Our main objective is like these 3 points, which includes these binary classification target, operation with delays, which are basically greater than 25% are we will label it as high delay rates, and our goal is to prioritize recall because to it is always better to raise an alert than rather than missing a true delay. So, what metrics we have used for performance, like what will be the judging factor of this? That will be AUC, ROC, recall, and F1 score. And the balance evaluation will be based on these three outcomes. There it comes, the data set. So, the data set we have been using is this airline delay cost.csv, and here is the details mentioned. So the key columns mentioned in this data set are total flight ARR underscore delay 15, which basically represents flight delayed by more than 15 minutes. And the delay causes are mentioned here. These these are the reasons like weather, NAS, security, late aircraft carrier, and identifiers like based on the categories we have been dividing. These are month, airport code, and carrier code. After cleaning, like after performing some basic operations and cleaning, we have roughly around 179,000 records covering multiple years and 29 carrier, like the 29 different kind of carriers we'll be having. So these are the basic results for this, and yeah. So this everything is mentioned over here, like what exactly is the column and what exactly is the feature. So uh, to make the data set analysis ready, we have like removed rows with zero flight, replaced a missing delay count with zero, and some columns like redundant field like carrier names we have dropped, standardized data types, and improved consistency. So after performing these basic operation onto these records that are here, so we have total of like around 178,997 clean records, and that is perfect for our EDA and feature engineering. Yes. So this got yeah. Yearly flight volume. And so basically, now we are coming to our EDA part, and here we have started with the year-wise data. So based on the data we are having, uh, we analyzed that 2019 had the highest traffic, and 2020 punched due to COVID. It is mentioned 2021 and 2020, 221 to 23. So strong recovery, but like higher average delays. And despite these traffic normalization, operational capacity remained stressed. What this indicated is that systematic inefficiencies and set direction. This will help in our modeling. Yeah. When we are comparing causes across the years. So we find out that the carrier-related delays dominate. Carrier-related delays dominated, and roughly around like 55% of the delays. Uh, and weather is the next most contributing factor onto this. So the best performers onto this are like Delta, which is approximately 18%, and United uh, around 19.5%, and American 20%. And we have our underperformance as depicted in the graph itself. And now coming to the seasonality and monthly trends, we have this is basically delay probability, how it is varying across months. So we can see like in summertime, June to August, and holidays, that time the delay spikes, and rest of the time in throughout the year, it is like basically lying around the averages, or like it has decremented. And approximately in the month of September to October, it is very like at the very lowest risk. So this shows the seasonal behavior and calendar timing strongly dependent on the influential delay patterns. And later on, we captured it as binary seasonal flags. So this, yes. So now we have seen this thing like the seasonal variation that we are using there. Now there it comes the target variable construction thing. No, so we computed that the total delay rate is equal to the array of like total arrival delay 15 by total flights, which basically depicted that the total arriving flights under than 15 minutes divided by total flight. And if the delay rate comes out to be higher than 0.25, then we marked it as 1. Then we flag it. Yes. Yes. So this threshold balances operational meaning and statistical distribution, and a minor class imbalance was handled through sample weights and training, and we have captured it through this training, and yeah, we have resolved that part. Uh, So from this stage onward, the focus shifts to the advanced feature engineering, and which will extract higher level of signal that why these delay occur. So we basically engineered our four analytical metrics. The first is delay rate metric. It will basically tell us percentage of flight delayed which are greater than 15 minutes, which will become the main predictive variable. Second is delay severity scoring. It categorizes the intensity of delay events, and the third is dominant cause classification, which identifies the top contributing delay factor for every record. And the fourth is controllability ratio, quantifies how many delays were airline control versus how many were external. So this will help us to cover all the correlation between operational and environmental factors, and which will later be linked, revealing cascading dependencies with daily operations. The next is operational drivers of the delay event. Now, to capture these operational pattern, we built several structural features, right? Like dominant delay cause, and with basically we aggregated all delay types into a single categorical field. And the other one is this flight volume tier. It is a quantile based grouping that will tell us about the congestion and intensity at an airport. And the last one is like outlier detection flag. We basically created a flag that will identify abnormal delay behavior using IQR deviation. Now, the biggest insight we got from this part is that the late aircraft appeared most often as the dominant cause. Like, yes, that now the finding in the validate the hypothesis that one delayed flight frequency triggers another is a classic propagation effect. That how airline network works. The next part is feature engineering for the delay drivers. So then we categorized every delay into four buckets. These are the four buckets mentioned over here. The first one is this carrier delays. The other is weather delays. Then the NAS delays, the late aircraft. So carrier delays, it is basically crew or maintenance issues. Whether it is external weather influence, we can directly interpret by the name itself. NAS delays, National Aviation System, or basically it is air traffic or system congestion delays. Late aircraft, this is inherited delays from prior flights. Okay, yeah. So these separation help the model distinguish controllable versus uncontrollable events, which will improve interpretability and make the output operationally actionable. So then we come on to the part where we analyze seasonal patterns. Seasonal and temporal variation are major determinant of our flight reliability. We added binary flags for the peak of summer, like we earlier mentioned that the in the summer part, the flight delays usually go rises and because it is the holiday season and yes, so we added binary flags for them to encode cyclic behavior that month number were transformed using sine and cosine functions, ensuring that December and January remain adjacent in the feature space. Additionally, we computed rolling averages and lag features. Yes, additionally, this is the part where we calculated the rolling averages and lag features. And to encode this, we are taking we basically are capturing previous 3 month trends in delays and flight records. So this will give the model a short-term memory and a long-term memory, a seasonal awareness. The next part is operational ratios and contextual flags. Uh, To provide a context for this, we designed a ratio-based and classification feature such as is high volume airport and is low delay airport. And these are like the a few of the listed features that we have created. So we have also added a time index variable to represent a chronological order. All redundant column like raw delay count were dropped and data types were cast properly and weighing factors were finally initialized as sample weight is equal to controllable ratio plus one. We can find it out. So this prepared a fully engineered data set that we will be proceeding to use in our training process. And if we talk about that, what exactly is this feature, we can directly relate it to this formula mentioned over here. Like delay rate is a arrival delay 15 by arrival flight. Okay, late aircraft delay by arrival delay, and this is being mentioned the all the insight over here. So moving on to the next part, final feature and consolidation and readiness. So after working through a lot of uh, like features, what exactly to take, what exactly not to take, and to give importance, we have mentioned over these here. So after like consolidation, the final data set will be containing around 80,000 records, more than 25 engineered features. And what we are going to do exactly is, yes, so this is the part where we have like above 80,000 observation, 25 plus engineered features, and we'll be using an 80-20 train validation split stratified by the target class. And uh, essentially, we'll be using XGBoost Nave's categorical encoding, and we have avoided one hot expansion, improving like which will basically improve speed and preserving interpretability. Uh, so yes, now comes the part where the model selection part. Uh, for the model selection, we choose XGBoost because it is like for the it is proven good for the structured data. It models the non-linear interaction efficiently and handles categorically, and the native supports of sample weights for class imbalance. Other model like logistic regression or random forest underperformed on recall. That is why we are using XGBoost. So our basically objective is to maximize the AUC ROC and because it is the primary validation metric we are using over here. Next, the model training setup and what will be our strategy. Okay, the model is used and trained using a 80-20 stratified split to preserve class balance. The main hyperparameters include that we are using here is the learning rate is 0.05 and the max depth we are using it as 6. Regularization lambda is 1 and we are early stopping of 20 rounds with of no AUC improvement. Performance was continuously monitored on held out validation set to ensure stable, generalized, and prevent overfitting. Uh, Now coming to the part hyperparameter configuration and key hyperparameters. What are these? And the final configuration we've got basically it is stable and flexible. A small learning rate we have chosen as mentioned earlier, while the max depth we have taken is 6 to keep the tree ensemble compact and interpretable. So, L2 regulation prevent this model from assigning large weights to noisy features, but not departing from our main objective. The function was binary logistic, producing probability scores for high delay risk. Like we have mentioned it earlier, like we are using early stopping the model automatically stops itself when the validation performance is plateaued. Basically, it stables out to some point. And in short, the hyperparameter that we are using are tuned to such a level that the model is efficient, stable, and like it is operationally deployable. So after performing the model onto our featured data set, the model performance turned out to be the accuracy is this 87% and the recall which was our primary focus it turned out to be 74%. This is our precision F1 score and uh, based on the previous models we have deployed and basically we deployed a logistic regression baseline model in the background like I have done it and the all in all improvement from that is it was an increase of an 18% of recall AUC gain like improved AUC by 12%. That means basically our model detects roughly 3 out of 4 high delay flight before they occur, which is I guess decent. The this high recall ensure that the risky flights are rarely missed and a high AUC indicate that the clear separation between risk classes. So this basically makes our model like precisely accurate and practically reliable also. Now, coming to the part, this is also the result metrics I've shown in detail. Like these are the classification report, and these are all the evaluation metrics we had used. This is on the weighted data set that we have engineered. Confusion matrix is here. IUC ROC curve I have mentioned, and this is all the details about the confusion matrix, like true negative, true positive, false positive, and false negative. We can all encounter these values according to these metrics. And this is all there, what we'll say, all the description mentioned here. Now, uh, confusion matrix, we can explain it about this like truly positive, false positive for deployment. Basically, what basically this means is like the threshold that we are prioritizing over the recall. Like we'd rather prepare than slightly miss a real delay event. So this helps us gain the true positive event. Now, now comes the model explainability part with SHAP. Now, to make model transparent, we use SAP, which basically means shapely additive explanation to identify which of the features were drive like which were truly predictive. The top global drivers included. First, we can see over from here, late aircraft count, strong contributor. It is a strong contributor, and from the feature itself, it shows a very cascading delay effect. Weather delays, seasonal patterns, and basically at a very high risk, predictably, and a holiday seasonal flag. Travel surges to correlate with operational margins. So SAP analysis, this helped us our to convert our numerical importance to actionable intelligence. For example, SAP, if it shows high influence from late aircraft count, airlines and can buffer time on reserved backup aircraft. So the explainability is basically just that it is more interpretable and it directly informs us in terms of decision making. Now come the feature importance and the feature impact and narratives. So basically, what we have concluded from this is that there are four major factors for this. The first one is that late aircraft count. The same aircraft that is arriving late directly delays the next departure. Second is seasonal congestion during holidays, airspace saturation and crew fatigue amplifies risk. Third is high volume airports and even minor disruption can cascade through this greater network of airports. The last we have concluded is carrier resilience, that the performance difference reveal the operational strength and recovery efficiency. So this is our takeaway from that that our model doesn't just predict, it is contextual insight. It gives us the contextual insight that why delay happened and where to act. And next part here is error and bias diagnostics. So we analyzed our segment-wise performance. So to ensure fairness and consistency, we observed that airport level under prediction at smaller regional hubs, it is basically at a very low predictive rate, and this can be improved. The second part is carrier specific skew. This tells that model accuracy was slightly higher for large carriers. The third and last one is temporal variation, and this temporal variation during extreme weather seasons we can see. Uh, other other reasons we can also include as it will come under the mitigation part. The basically these are the segment specific thresholds, the probability calibration, and rolling window validation. These are mentioned all here, like what exactly is the reason behind this. And now coming to our model limitation, that which is basically every predictive system has some limitation. So in order to justify the limitation, we have the first one as temporal leakage. Since training and validation aren't very strictly time separated, but yeah, we have done it on our feature dataset. So this can be one. The second is that the model still lacks some forecast data and it only uses the historical weather data. So we cannot rely on to the historical weather data as a whole. The third, which can be seen as the data sparsity at smaller airport, because the data is not quite accurate and it is present in a very less abundance. So yes, and lastly, we can conclude it by seasonal distribution, and this might like degrade the performance over time because seasonal distribution it varies time to time, and addressing these uh, on the rolling window and integrating live weather and ATC input, we come on to our next part, that is our deployment vision. Our deployment architecture is designed for both batch and real-time inference. The train model is containerized in Docker, served in the REST API, and integrated into a streaming pipeline for live flight updates. The integration points include crew scheduling, gate assessment, passenger communication, and apart from this, the monitoring dashboard will track the things like the IOC drift should be greater than 92%, like the 92% is set as a threshold for that. False negative alarms and data freshness, like it should be less than 15 minutes. So these all things are mentioned over here. And for our future correctiveness, uh, we can enhance these accuracy and adaptability to several future direction which are planned as like these temporal computer vision, live data signals, connected flight graphs. These are basically future enhancement which we can still work upon, and this improvement will make this model system smarter and faster and autonomous. Yes. So in concluding the project, what we have summarized is that we built a full end-to-end ML pipeline for our flight delay prediction. The model achieved AUC of 0.92, basically 92%, and recall of 74%, demonstrating that the strong discrimination and reliability. Using SAP, we added the explainability for real-world interpretability. Now, finally, the deployment plan ensures scalability and measurable optional ROI. Like, however, it is not deployed right now, but the model that is being working in the backend, that is fully built. So this project is like fully this project basically shows how data science can move beyond analysis in real-time operation intelligence to avoid aviation sector. Thank you.